We'll start again.
Thank you.
Welcome to the Paint Plastics OA Team's QCC entitled The Window of Time. Our team's safety commitment is we will ensure an always safety first mindset. And in the background behind me is our paint shop's newest, largest new model expansion area called RDS, which stands for Roof Ditch Sealer. This area had incurred many conveyor faults, resulting in a very large amount of downtime. This was the main area that we focused on for our problem-solving activity in relation to our KPI target of productivity. Now let's meet our team. Our circle leader and team leader, David Sanchez. Our theme leader, Richard Montesioca. Our theme member, Adan Gonzalez. Team member, Rudy Navarro. Team member, Danny Sarmiento. And team member, Ta Yu Tu.
Before QCC, we evaluated our team members' QCC level, came up with the development focus items for these team members. We also set a target for our circle dynamics and our technical capabilities for the team. I will pass it over to Richard.
Thank you, David. Roof Ditch Sealer, 32A station. Here we have a body making it onto 75 lift table. We'll transition over to 77 lift table, then make it into the robot cell. This also controls all conveyance for RDS. Our theme selection matrix. We chose the window of time lift table motion faults due to the overall total points and the highest ranking. This also had the highest potential for success and the greatest impact to production. I will now hand it over to Don.
Thank you, Richard. Step one, clarify the problem. So our ultimate goal is to reduce downtime at 32A and improve overall plant operational rate. Our current situation is we have 55 minutes of downtime at 32A. Of course, our ideal situation would be to have 0 minutes of downtime. Our gap currently is 55 minutes. Because RDS is the bottleneck area of the shop, the 55 minutes of downtime causes equal amount of full time to body wheel, overtime over paint shop, and short time to assembly. Now I'll pass it to Danny.
Step two, we're going to break down the problem. Our gap at OP3-2A has 55 minutes of downtime per shift. We went down to this area, and for many days we looked at all the different faults that were happening down there in this area. We saw that the lift table motion faults was giving us 40 minutes of downtime per shift. So we went with that. We know there's 2 lift tables in that area, and the 75 lift table was giving us 30 minutes of downtime. So that was our point of detection, the 75 lift table motion fault when motion exceeds the cycle time. Here we have the 75 lift table. When this lift table goes up, it's supposed to stop at up end. As you can see in the video, when it gets up end, it just continues to cycle. When that cycles and it times out, that gives us our motion faults. So we prioritize our problem at the point of occurrence. Excessive downtime at OP3-2A was caused by motion faults at the 75 lift table. Step 3, we set the target. We went to eliminate the 75 lift table motion faults at OP3-2A. We wanted to do it by December 1st of 2021. What we had 30 minutes of downtime at this lift table. We wanted to bring that down to 0. Our overall impact would be, we have 55 minutes of downtime in that area. Lowering that, we would get to 25 minutes of downtime. Our target was very challenging, but this issue created a lot of downtime, and we needed to solve it quickly. Now I give it to Rudy.
Thank you, Danny. So when determining the root cause, we determined that the majority of the downtime at 32A was caused by lift table motion faults. We looked at man, material, and method. All those were eliminated. We went to machine, and we could see that the lift table was cycling repeatedly. We did a go and see. In these 2 videos, we see a good lift table and our problem lift table. The 2 components that tell the lift table whether it's going up or down is the cam disc and the photo eye sensor. So in the first video, you see the cam disc turn the window enters the photo eye sensor, and the lift table stops. Here we drive it again, the window enters the sensor, and it stops. That's our proper operation. Here we have our 75 lift table, same components, same operations. So here when the cam disc turns, the window enters the photo eye sensor, but the lift table continues to cycle. That's a no good condition. So we went to the three most common failure components: the motor brake, photo eye sensor, and the contactor relay. Here's a graphic of those components. So the first one we looked at was the sensor. There was some debris on the sensor. We cleaned that up, really no change. We replaced it, still minimal change. From there, we went to the contactor and the relay. We checked both of those components. We found some loose wires, fixed all that up. We replaced both of those components, still minimal change in downtime. That led us to the motor and the brake. So we checked the brake, we adjusted the brake gap. We actually replaced both of those components, but still minimal change in downtime. So after all this work, we still have not gotten the results we wanted. We have not hit our target yet. We're getting a little frustrated at this point because we've done a lot of work already, and we decided that further investigation was needed. So once we looked at all these components, we realized we had overlooked PLC. So we went there next. We saw that it was an older version and it had a lot of logic installed because of the RDS expansion. So we upgraded it to a newer, faster PLC. We also confirmed all the signals to the PLC using a time chart. Still minimal change in downtime. So now we're really frustrated. We've thrown everything at it and it's still, everything seems to function, but overall continues to fault. At this point, we start looking at signal paths from the sensor to the PLC. That's accomplished through the device net cable. It's part of a larger network. So here to explain networks is David.
Thank you, Rudy. So here we have Group 8 device net network. This is, for example, for our primer booth. We have the main Group 8 master control panel, which has our PLC in it. We have a sub panel called 8-1. These are the node addresses that have all these sensors attached to them. This network here has a minimum of about 40 feet in length. This is our device net communication between both of them. This allows for a fast scan speed with these short cables. Pretty standard. On this location, we have this lift table cam motor, just like at the RDS. Here we have the cam disc that rotates with the motor. The sensor is looking at the cutout. So the sensor communicates to the device net node through the device net cable to the PLC. The PLC makes its logic decision. It comes back through the same device net cable to the node, to a relay, to the brake of the motor, stopping the motor with the sensor being in the window of the cam disc. This is a good condition. Our next section is the problem area. This is Group 3 RDS area. So before the RDS expansion, this was our existing condition. We had one Group 3 PLC with a device net communication to all these nodes, all these subpanels. After the RDS expansion, this equipment was added in, more subpanels, more node addresses, more equipment. This problem area that we're talking about is 320 feet away. This complex network results in a long device net cables with a slower scan speed. So on our no good condition at this 32A, we have the same lift table that we're talking about. The same motor drives the cam. The signal layout is the same. It's from the sensor to the device net, through the longer cable, to the PLC, back through the same device net cable, to the node, to the relay, and to the motor brake. But by that point, it's too late. We're out of the window. So the motor cycles one more time till it faults. That is our no good condition. So getting back to step 4, our network and our PLC control signal did not get to the drive quick enough to catch the cam disc timing window. The device net scan time increased due to the network expansion from the new model equipment. Our statement stating that after investigation of repeated cycling, we determined that the window on the cam disc moves past the sensor before the output signal can arrive due to a lag in network speed. Now I give you Tom, the next step.
Thank you, David. Step 5, develop the countermeasures. After countermeasures, step 5, develop the countermeasures. Step 1,
First countermeasure, install additional PLC to a separate network. The cost was $500,000 and the lead time was 3 months because it's a major changeover and it is a big project. Second countermeasure idea was to increase communication speed on our network. Our network is already set to maximum speed, and the only way is to upgrade our network cable to fiber optic. The estimated cost is over $600,000 and our lead time would be 6 months. The last countermeasure was to modify cam disk by cutting the window on the cam disk wider. The cost is low, it is feasible, and our problem can be solved in a short time. First and second countermeasure was eliminated because of cost and feasibility, so we chose the last countermeasure. Action plan. We consulted with original equipment manager about cam disk modifications. We modified. We then effectively communicated with production, management, and maintenance personnel about the change point. We installed the cam disk. We ran many trials, and we made adjustments as needed. We confirm and follow up with the whole process. Here we see our master fabricator putting his skill to work for a perfect modified cam disk. Now I'll give you Richard.
Thank you, Tom. See countermeasures through. Before RDS expansion, of course, there was no downtime. After RDS expansion came online, OP32 overall faults immediately increased to 55 minutes. Here we have version 1 OEM disk from Tsubaki that has a 14mm gap window. As you can see, out of the 55 minutes, we have 40 minutes that are attributed to the lift table itself. We did make several checks and adjustments to the equipment and the lift table and all supporting equipment, but that had minimal impact. So at this point, we figured the network could be the culprit. So we decided to take the disk and make version 2 with the 17mm gap. We placed it online. As you can see, we made a significant drop in overall faults down to at least 10 minutes of faults. But at this point, IR lamp expansion came online. Then the unexpected happened. We had more device nodes that needed to communicate with Tsubaki. This had a negative impact on our overall improvement. We increased our faults up to 35 minutes at this point, but we had a path forward at that point. So we took to version 3. We modified the same disk to 25mm gap and we placed that online. At that point, we saw another significant drop, but we had not met our target yet, so we continued on. Version 4, our final disk. We had a 30mm gap with a corresponding 20mm gap window, and that was placed online. At this point, we had reached our target. We are now at 0 faults for the lift table faults. Good condition after the countermeasure. Once we received a signal for the cam disk to rotate, even with a lag in the network, we were able to meet the signal and remain in the window due to the notch that was placed online. So in summary, we ended up with version 4 with a 30mm gap for the up end window and a 20mm gap for the down end window. That was placed online. We gained 0.17 tenths of a second to end up with a 0.34 tenths of a second for our scan time. I now hand it over to Adon.
Thank you, Richard. Step 7, confirm results in process. So you can see here, 75 lift table motion faults. We started with 30 minutes. We were able to bring that down in November to 0 minutes. Over here, 328 overall faults, as we mentioned, was 55 minutes. We were able to bring that down to 25 minutes. That's a direct reflection of eliminating the lift table fault. After we yoke attend to the 77 lift table fault, we were able to bring that number down to 15 minutes. So not only did we hit our 30-minute mark, but we were able to get 10 more minutes out of there for 40 minutes total of downtime reduction eliminated and a 10% OA improvement. Continuing on, cost savings. So if we had a contractor install any of the 2 options, it would have been anywhere from $500,000 to $600,000. But since we decided to tackle this big problem, we pretty much did it for $120. Not to mention but the $95,000 in overtime savings. After we implemented our fix, we reduced that down to 0. Step 8, standardized successful process. So we did a lot of follow-through tasks. We yoke attend through our paint shop, through the big network groups that we had. and we were able to eliminate all lifter cycling issues in any of those corresponding groups. Not to mention that in our group 7, we were able to solve a lift table issue that we had since SOP 2005, which that was an extra 35 minutes of downtime per week that we eliminated. Continuing on, so we're going to discuss with our OEM manufacturer to use the modified cam discs that we developed for a global use, not only just for Toyota, but just globally. We're going to discuss with Team NA to do a network capacity study because I don't think they realized adding as much as they did to 32A, the unexpected happened, right? Scan cycle times were very fast, so large, couldn't keep up. So we asked them to do that for every new expansion project. We actually developed a network scan time calculation workbook, which is here, and we submitted that to our BPAC so that everybody in globally Toyota would be able to see that and utilize that to do their own calculations. And now I give it to David.
Thank you, Don. So continue with our review and future plans. Our QCC level, we exceeded the technical development target, but still have some gaps at Circle Dynamics. We will focus on it on the next QCC, but we did go from a Zone C to a Zone B. My reflection on this is I have learned to respect that the time also plays a big part in network capacity and network signals.
Thank you, David. My reflection is I've learned to appreciate the network simply because we ourselves can cause a communication lag, which can turn into a big issue. So now we'll be able to study it further.
I learned from this QCC that signal paths are very important, especially when it comes to troubleshooting components and controls.
From this QCC, after I understand the root cause, I learned that a small detail on the cam disc can be a solution to a big problem. I just want to say how fun it was to implement these 8 steps of QCC into this very large problem that we had.
After the many years of being here at Toyota, I've been able to troubleshoot mechanically. This was the first time I've been able to troubleshoot the network, and I learned a lot from this QCC. Thank you for watching our presentation, and now we're ready for questions and answers.